Today we're doing some more Calculus 2 practice problems focusing on parametric equations and calculus. So in the last video we looked at parametric equations. We looked at eliminating the parameter, sketching the curve represented by the parametric equations, and also indicating orientation. So now we're going to use all of that knowledge and skill set and throw in some calculus. For example, these are parametric equations where x and y are both functions of t. Right, and they want us to find dy dx. So we either have two options. What we can do is, this is also an equivalent equation. We can just divide both dy and dx by dt, because we could just cancel the dt and dt with a keep change flip. Right, so we did not change the value of this equation. This is going to be the general strategy in solving these derivatives with parametric equations. We can just take the derivative of y with respect to t. A chain rule would cause there to be a negative 1/2 out front. We can divide that by the derivative of x with respect to t, a 2e to the t. Finally, a little bit of simplification, that e can come down and we can add them together to be an e to the 3/2 t. Right, so we did this without eliminating the parameter. And I'll show you in the next one how we can eliminate the parameter and avoid this mess, right? But before I show you that, let's look at finding the second derivative using the same strategy. If we want to find the second derivative of y with respect to x, we can just find the derivative of y with respect to x and multiply it by the d over dx, right? And we know that dy over dx is just y prime, like what we found in the last problem. We had found y prime, which is just dy over dx, right? So we can turn this into a dy prime over dx and evaluate it the same way. Take y prime, which has no t's in it, right? There was, well, it did. Take y prime, derive it with respect to t, right? Y prime has t's in it, we're going to derive it with respect to t. And also take that dx that is in the bottom here and derive that with respect to t. Right now we could cancel this dt and this dt and get the answer we need. This is going to allow us to solve for it. So if x equals the square root of t and y equals 3t minus 1, what is d squared y over dx squared, right? So what is the second derivative of y with respect to x? Well, let's find the first derivative and we'll plug it in there. So the first derivative, dy over dx, it's the same thing as dy over dt over dx over dt. So the derivative of y with respect to t is 3. The derivative of x with respect to t is 1/2 root t on the bottom. And we could rewrite this to be 6 square roots of t with some simplification. Okay, now we're going to plug it into this formula. But we also need the derivative, the d over dt of this y prime. This right here is going to go into the numerator right here, right? So what is the derivative of y prime with respect to t? Well, this is really a 6 to the t to the 1/2. So the 1/2 is going to come down and we're left with 8. And then we're going to subtract 1 from the exponent. And we also need the derivative of x with respect to t. So the dx dt, we had already said that was just 1/2 t to the negative 1/2, right? That is the derivative of this square root of t. And we can divide those, right? We can put the 3t to the negative 1/2 on top and the 1/2 t to the negative 1/2 on the bottom. As you can see, the t to the negative 1/2 is going to cancel that t to the negative 1/2, and we're just left with 3 divided by 1/2, which is 6. So this is the general strategy. What we're going to do, we're going to find y prime, right? Derive it with respect to t, and divide that by dx dt. Or we can do what's called eliminating the parameter, which we looked at in the last video. If we want to find the second derivative of y with respect to x, can we write y is a function of x, meaning if x equals the square root of t, can we say that t is the same thing as x squared? And in that case, y equals 3t minus 1. So really, y equals 3x squared minus 1. So let's find y prime. Y prime is 6x, and y double prime is 6. So we get the same answer. 1 is a lot easier, right? Eliminating the parameter in this way is a lot easier. But we're not always able to do that, so we have to know how to be able to manipulate these derivatives in order to get the right answer. Okay, so let's look at now some more calculus. This is a good calculus 1 refresher, is slope and concavity of these parametric equations. So remember, slope has to deal with the first derivative, concavity has to deal with the second derivative. So I have both of these equations here. So let's see, what is dy over dx? Well, the same thing as dy over dt. Let's see, what is the derivative of y with respect to t? That 1/4 is going to stay there. And then we have a 2t, right? That is the derivative of y with respect to t. And what is the derivative of x with respect to t? It is a 1/2 t to the negative 1/2. Right, so now we have this 2 and this 4 make a 1/2 that cancel with the 1 on the bottom. So we just have t over t to the negative 1/2. So we can just subtract them. We have t to the 1 minus negative 1/2. Same thing as t to the positive 3/2. So this is the first derivative, dy over dx. And remember, the second derivative turns into this formula, which we just proved in the last problem. We're going to derive that y prime. That's going to be our numerator. So the 3/2 comes out front. We subtract 1 from the exponent. And we're also going to take the derivative of x with respect to t again. We said that was 1/2 t to the negative 1/2. And let's see, the halves cancel each other. So we're just left with a 3t, right? Because we have a t to the 1/2 minus negative 1/2. Those 1/2s add together to just become 3t. So this is the second derivative. This is the first derivative. But how are we going to use that to find slope and concavity at this x and y value? You can see that our slope and concavity functions are t, but they didn't give us a t value to evaluate it. They give us an x value. But we know that x is the square root of t, right? So, in other words, 2 is the square root of t. Or t would be 2 squared, which is 4. Right, so we know that we're really evaluating at t equals 4, but let's verify. Let's make sure that when we plug in 4 into y, we're going to get a 3, because this value should also correspond to t equals 4. What happens when we plug in 4 into y? Y evaluated at 4 for t. Leave 1/4. 4 squared minus 4. So that's 1/4. 12. 16 minus 4 is 12. And 1/4 times 12 is 3. So we did get that same, or that y value of 3 at t equals 4. So the ordered pair 2, 3 happens at t equals 4. Right, so we did a lot of that with the table in the last video. So finally, the slope at t equals 4 is just t to the 3/2 evaluated at 4, right? So we have 4 to the 3/2, which is the same thing as 8. So that is the slope of the function at t equals 4. Or by t equals 4, this is the same thing as 2, 3, right? What about concavity? Concavity at 2, 3 is plug in t equals 4, and we get 3 times 12. Nope. 3 times 4, which equals 12. What does that tell us about concavity? Well, since the second derivative is positive at this t value, concave up. When the second derivative is positive, the graph is concave up. So we used this information to determine that the slope at t equals 4 was 8, and that the graph is concave up at that point. Okay, so let's look at another application. Remember these from Calc 1, finding the equation of a tangent line to the curve represented by the parametric equations. Well, in order to find the equation of a tangent line, we're going to need point slope form. We did this a lot in Calc 1, which means we need an x1, a y1, and a m. Well, in these two ordered pairs, they give us an x1 and a y1, an x1 and a y1, right? So all we're concerned about is finding m, where m is just the derivative, right? So let's find the derivative. The derivative is dy dt, which is 2t minus 2, over dx dt, which is 2t. So this is the slope function. But notice they're asking us to evaluate it at x values, which is okay. That just means that we need to find out what t value this point occurs at so we can plug it into our slope function. So let's see. If x equals t squared minus 4, what t value would cause it to be 0, right? T is either going to be plus or minus 2, right? Because a negative 2 squared minus 4 still gives us 0. So t is either going to be plus or minus 2, and we're going to figure out which one by looking at the y value. We also want the y value to be 0. So what happens when you plug in positive 2 in for y? You get a 4 minus 4 equals 0. When you plug in a negative 2 into y, you get a 4 plus 4 that does not equal 0. That tells me that the t value of 2 corresponds to this ordered pair. So this is t equals 2, t equals 2. So for the ordered pair 0, 0, t equals 2, and we have y minus 0 equals, what is m? It's just this equation right here evaluated at t equals 2. We're going to get 4 minus 2 on top and 4 on the bottom. And then we have that x minus 0 as well. So the equation is y equals 1/2 x. This is the equation of the tangent line to the parametric, or the curve represented by the parametric functions. So the only thing that's going to change for this one is, of course, we have that y minus 3 equals m times x plus 3. Right? We just have to figure out what m is again. Well, we have the function for m. We just need to know what t value to evaluate it at. So what t value would give us a negative 3 for x and a positive 3 for y? Well, once again, I see that since x is t squared minus 4, we want x to equal negative 3. That means t is either going to be plus or minus 1. If it's a negative 1, we'll get negative 3 for x. And if it's a positive 1, we'll get negative 3 for x. So we're going to have to use the y value. We want the y value to be 3. So what happens when you plug in positive 1 in for y? You get a 1 minus 2. Well, that gives you a negative 1, right? So that's not it. When you plug in negative 1, you get a 1 plus 2, right? Because negative 2 times negative 1 is positive 2, and 1 plus 2 does equal 3. That tells me that the t value, negative 1, corresponds to this ordered pair, right? This is t equals negative 1. So that just means that m is once again, the slope function evaluated at negative 1. We're going to get a negative 2 minus 2 on top and a negative 2 on the bottom. So we have a y minus 3 equals 2 times x plus 3. And we can leave it like that. That is just the, well, I guess we could put it into slope-intercept form. We're going to be 2x and a plus 9, right? So that is how we do the tangent line to a curve represented by parametric equations. Okay, so let's also look at one other, and we could do a lot more with this, right? We could look at horizontal tangent lines where we set the derivative equal to 0, t values where the derivative equals 0, and we could do a lot more applications that are just really a refresher from Calculus 1, but this is the extent of the parametrics, is like figuring out what t value to use and also finding the derivative first or second in terms of t. Okay, so let's also look at one other application with calculus, except that was calculus 1. This is calculus 2, right? Arc length is a calculus 2 concept, and we have an equation for arc length in parametric form. It is the integral from a to b, square root still, except now the square root has the dx dt squared and the dy dt squared. So find the arc length of the curve represented by the parametric equations. X equals 3t plus 5, y equals 7 minus 2t, and we're going from negative 1 to 3. Well, that tells me that the integral is from negative 1 to 3. Square root, what is dx dt? Dx dt is just 3, and dy dt is just negative 2. So we have a 3 squared, right? This is dx dt. And we also have a negative 2 squared, right? This is dy dt. We also have a dt. So this is the integral from negative 1 to 3, square root of 9 plus 4, or 13 dt. That's an easy integral, right? It's just square root of 13t evaluated at 3 and negative 1. So then we also have, or let's see, we have square root of 13 times 3 minus square root of 13 times negative 1. So that's just going to be 4 square root 13. That's going to be our arc length. So we could look at some harder problems, but this is the extent of the parametric, right? All you need to know is that it's dx over dt squared and dy over dt squared. And if you had any questions about arc length, I have an entire video on that and about how we can solve some of these integrals that can be pretty messy. So for the purpose of this video, we're only concerned about finding dx dt and dy dt, and we can just plug the rest into our integral capable calculator. So that is about the extent that you'll see of calculus and parametric equations. Again, horizontal tangencies, vertical tangencies, equations of tangent lines, all of the signature Calc 1 stuff will come up along with arc length. So it's really not too bad if you have the parametric stuff down. Probably the only hard part is this second derivative equation maybe, but also you can eliminate the parameter like we did in the second example if possible. So that is how we do calculus and parametrics.